It's great to be here this evening and to meet so many wonderful friends and relatives and former students, some of whom I recall teaching 35 years ago. So it is a real wonderful journey back to those early years here at the University of Lethbridge. I will try to be relatively short in my explanation of the scientific and theoretical aspects of my research and show you some of the practical aspects and interpretations that we've been able to draw from the many sites where I have worked. So first, I'm going to show you a bit about the global climate archives in mud and rocks. So I'm still working in mud, even though I tried to get away from that on the irrigation farm. And I've used a magnetic recorder. We're all familiar with magnetic tape recorders, although my students, I don't think, know what a magnetic tape recorder is anymore. But certainly the Earth's magnetic field operates like a tape recorder and has some memory of what has happened on the surface of the Earth. And my job is to try and listen to what that ancient tape recorder is telling us. I was born, as was mentioned, in the Galt Hospital here, BSc in Lethbridge, MSc in Delft, and PhD at Queen's. And then I did some postdoctoral work at the University of California, Davis, and took a teaching job at the State University in San Francisco, and then returned back to Lethbridge, which I thoroughly enjoyed. People born in the 50s have lived in 7 decades, 2 centuries, and 2 millenniums, and we're not even that old yet. I thought that was a pretty good description. I received my first introduction to geology, I suppose like many kids growing up in the southern Canadian prairies, by having a family camping trip to Yellowstone Park. And there you see some of the basalts, which I was attracted to immediately, and I've since then drilled many basalts, including those in the Yellowstone area. Mud wrestling was one of the favorite pastimes in the sweet little town of Picture Butte. It meant digging a hole and filling the bottom with a bit of drilling mud and water and throwing in a hog, pig, and then seeing who could be the first to wrestle it out of the mud hole. And of course, for this occasion, you would dress up in a 3-piece suit. So this was another reason I felt I should go to the University of Lethbridge and get away from all this mud. But I haven't been very successful. As you can see here, I'm still shoveling and picking away at mud even this year and enjoying it immensely. I started off as a history major, wanting to be, of course, a social studies teacher. And I often think, I wonder what my life would have been like if I had gone on in history or some other job. I remember telling my parents I wanted, when I grew up, to be a comedian, and they said I couldn't do both. So I decided to stick to geography. One of the great pleasures indeed is teaching students, and one of the courses I teach is geomorphology, the landforms of Earth. And of course, it's a delight to use the examples from the many places I've been to, courtesy of the Canadian taxpayer, to do research and at the same time bring back materials that I can use in my classes. The students, of course, illustrate their field trip reports with the many beautiful examples of landforms we have right around us. Just think of the many sites you could take a student to here. Of course, the Rocky Mountains, or the Rock Pile as we call it, to the west, Head Smashed In Buffalo Jump, and the Porcupine Hills, the Milk River Canyon, Red Rock Coulee, the Cypress Hills, and the many beautiful valleys. So students have an opportunity to not only learn in the classroom, but also to participate in field trips and field work, as well as research work. So they get a good mix of teaching and lab experience. What is the overarching goal of my research? It's basically to determine the timing and extent of glaciations in the northern hemisphere. And really very little was known about the glacial history of North America. And so the main reason for that was that there was no easy way to date glacial deposits, and very few people had looked at outcrops that showed more than just the surface deposits. What are some of the natural causes of climate variation? Well, there are probably the main reason are orbital variations in the Earth's tilt and eccentricity of its orbit, the precession of its equinoxes. This affects the receipt of solar radiation, how much sun's energy falls on our planet. I'll show you a few more examples of that. The amount of land versus ocean, and that varies with sea level, of course. The orographic situations, the heights of mountains affects the interception of moisture, the distribution of ocean currents, the surface reflection, and especially super large land areas like Eurasia, Siberia. If snow lingers there for a few more weeks, for example, in the spring, it can cool down a relatively large piece of real estate of this planet and affect the size of the monsoons to the south. And so probably some of the weather patterns we see changing from year to year are related to what simply is happening on these very large land areas, especially in the late winter and early spring. The composition of the atmosphere changes somewhat from volcanic eruptions, gas, dust, windstorms, fires, smoke, and so forth. So those are the main drivers of climate change. On this little diagram, I've shown you from the top the historic records, which of course are those that are taken from instruments and you and I can readily access. They're very accurate. They've become more accurate with time, and many of these are now automatic data recording procedures, and a lot of information is being obtained from satellite imagery. But once we get beyond the sort of first thermometer and wind vane, we have to look at other records, and those are called proxy records, approximations of what the weather and climate was like. And you turn, first of all, to tree rings, because tree rings give you a measure of how much moisture fell during the growing season. Or you look at dripstone in caves, or you look at pollen that has been preserved in sediments that tells you what sort of plants were growing. And you can look at ice cores, for example, or you could look at ocean cores. But the longer and more extensive records require you to look at geology, the deposits laid down by glaciers, the thick soils that have formed during warmer periods, and so forth. So the geological record gives us perhaps the most extensive archive of climate and is probably one of the more difficult ones to read. The methods for short-term climate reconstruction, we're talking in the order of hundreds or thousands of years, involve radiocarbon dating, the growth of tree rings, the science of dendrochronology, speleothems, cave dripstone, corals, coral reefs, the deep sea sediments, probably the most valuable archive we have, and ice cores. Those two also give us a record that goes back hundreds of thousands of years. That map shows the sites where we have tree ring records. That is most of the mid-latitude areas. The ice cores obviously come from Greenland and Antarctica, and the corals from the warmer waters, Bermuda and off the Mexican coast and so forth. So in the case of tree ring data, the width of the ring is important, and you have early wood and late wood. The early wood forms in the spring and early summer and is the main growth spurt of the tree, and then the late wood is the late summer and early fall and can be and is usually darker, slower growing. And then there are some false rings which are easy to identify, as you can see on that slide there. So you can count the rings and actually convert some of those ring widths and so forth into temperatures by looking at what tree rings today look like, and you know the instrumented climate record, and we know that back at least 100 years or more, and so we can compare modern tree ring records with modern weather records and extend that back in time. Trees go back, 6,000, 7,000, 8,000 years. Bristlecone pine in the White Mountains and the black oak in Germany, longest living trees, but you can also use dead wood. The rings are still preserved. Some of the old beams in cathedrals in Europe go back a very long time. And of course the trees that have fallen into bogs and into shallow coastal waters from perhaps tsunamis are nicely preserved, and those go back to 40, 50, 60,000 years. So you can get old trees and work out this beautiful dendrochronology. A scientist at Regina, Dave Sachin, has done the most extensive tree ring study from the Porcupine Hills, Cypress Hills, Sweetgrass Hills. And this is what he has done. He's converted the tree ring record to water discharge in the South Saskatchewan River at Medicine Hat, back to 1100, to the Dark Ages. And the blue are surpluses of water over the mean, and the reds are deficits. So the river is above average in the blue zones and below average in the red. And you'll see that there are some pretty major periods of water deficits, aren't there, in the South Saskatchewan? And even in the Little Ice Age, when Europe was cool and glaciers were advancing and it was wet and miserable, on the prairies, at Medicine Hat at least, rivers were lower than average for 2 very big blocks of time. So climate is very different in different parts of the earth. You see the dirty 30s, the Dust Bowl era, marked there at the bottom, the little red part, the 30s, a very dry period. So what we see from this tree ring record is that we have extremes here in southern Alberta. And the average discharge of the South Saskatchewan River at Medicine Hat is about 300, 400 cubic meters per second. And you'll see that that variation shows 100 and 150 meters of variation. So a half less or a half more than the mean is substantial, and especially today if you're irrigating from that river or dependent on it for potable water. So tree ring records give us a very beautiful picture of what's happened, at least here in the last 1,000 or more years. And he's working on extending that tree ring record back. And those are from the limber pine and lodgepole pine and so forth from the Sweetgrass Hills, Cypress Hills, Porcupine Hills, and the foothills. Dripstone in caves, beautiful long archives, preserved. They basically take the meteoric waters that fall on the surface and provide the geochemical signal of that in the cave where it slowly grows. And many of these cave stones show annual growth layers. The other thing you can do is carry out all sorts of chemical analysis on these dripstones that tell us something about temperatures in the past. So there are variations in their rate of growth, and they reflect the environment that exists up above the cave, the type of vegetation. The pollen can be preserved in this calcite, and you can date these with thermal ionizing mass spectrometry and of uranium series material in the calcite. And so they are an important paleoclimate archive, a record of past climates. And some of these caves have had dripstone growing in them for hundreds of thousands of years. We have beautiful big caves to the west here in the Crow's Nest Pass that have been studied. The Nahanni Caves, Nahanni National Park, probably the most extensive record, and they tell us a lot about the climate of Canada over 100,000 or more years. And you see annual growth, accumulations, and they vary depending on how wet a year it was and what the temperature was. Corals tend to have also, like dripstone, annual accumulations of light and dark zones as shown in this picture, so you could use corals. Ice cores, extremely valuable. Again, you can count annual layers, and especially in the upper part. Lower down, the ice gets compressed more and more, and it's harder to see the layers. But the other benefit of ice cores is that in the ice itself are little air bubbles, which contain the gas of the time the snow fell and was converted to ice. And you can analyze those air bubbles for oxygen 18-16 ratio, which is a paleothermometer, tells you what the past temperatures were when that bubble was incorporated in the ice. So we have then the short-term records that I've just shown you. But now, what do we have in terms of longer-term climate records? Well, we have to turn to geological materials, rocks and sediments on continents. Those are the best for us to look at because that's the hard evidence of what happened on the surface that you and I live on. Was there a glacier here in the Lethbridge area? Or was it warmer and were there dark brown soils forming or even red soils? So we need to know what happened on land. The ocean is a fantastic record, but the land record is going to be the most definitive in terms of giving us details. So these are deposited over long periods of time. I've worked in the materials that are highlighted in turquoise. I don't know if you can read this fine print, but It includes glacial deposits, wind-blown sediments, the thick loess accumulations, for example, of China, and lake sediments in the Great Lakes. And I've also looked at the fossil materials in these sediments as well as pollen. So I can't look at all the proxies of paleoclimate. Life would be too short for that. But I focused on the glacial sediments of the prairies. And of course, when you and I go to the valley walls here, we see these enormous clay cliffs made largely of ground-up material that the glaciers transported long distances from as far away as the Northwest Territories and even the Canadian Shield, and smeared down, much like peanut butter on toast, if you like, this sticky clay material let down at the base of the ice, and much of the prairie landscape looks like something that was dumped by a bulldozer, as you see in that middle image. The little hill on the lower left is a hummock. A hummocky moraine is the sort of rough deposit left by glaciers. And that hummock is interesting. It's near Shaughnessy, and it's recently been excavated. And so we can see what the inside of these hummocks looks like. And it's been a fascinating little study just this year to look at that. And you'll see that it has glacial tills, these muds laid down by advancing ice, but also lake sediments with varves. You see the annual layers there. Now, these sediments are only useful to us if there's something in there that we can date. Bone or shell or volcanic ashes, which are easily dated. And in the land record, you don't have a lot of datable material often. We've been lucky at Medicine Hat. There have been enormous amounts of bone found in the glacial deposits, and so we know a little more from the Medicine Hat area. What we do with the land record is we marry the magnetic time scale with the isotopic time scale. The isotopic time scale on the left there, the blue for colder and pink for warmer temperature spikes of Earth history, match beautifully with the geomagnetic timetable, time scale, which has been derived from Hawaii, where lavas are constantly pouring out and, like a tape recorder, recording the Earth's magnetic field conditions, the polarity of the Earth's field, and many other details. So the tape recorder is always on where you have lavas pouring out. So you have that magnetic record. And in the ocean, of course, sediments are always raining down, together with the small shells of animals from which we can measure paleotemperature using Delo 18, or the change between oxygen 18 and 16. So what you see in that paleotemperature curve at the bottom here, I've laid it on its side now, is that temperatures, the older materials are on the right side. As you go to the present, which is on the left side of that scale, things are progressively getting cooler. And we've been gripped into this phase of glacial interglacial cycles for a very long time. And these cycles have been getting longer and colder. So a few basics. We have the rocky planets near the sun. And these have the opportunity, at least, to have magnetic fields that are generated by the liquid material that slowly convects and rubs up against the solid inner core and the solid mantle, creating a magnetic field. And of course, at the same time, the Earth is rotating, so you get a helical movement, convective movement, where the lighter materials rise to the top and the heavier components sink to the bottom. So there's a constant interchange in this liquid core, and that generates our magnetic field, and that's what magnetizes things, and that's what I measure. I won't, these are simply too hard to read for me from here, and I suppose for you as well. So the Earth's field is basically a dipole, a bar magnet that extends through the center of the Earth. And the Earth is either normally magnetized with the North Pole at the top or reversely magnetized with a North Pole at the south. And the Earth's field goes back and forth from being normally magnetized to being reversely magnetized. And that record is recorded wherever lavas are pouring out. The Earth's magnetic North Pole is never at the same place as the true North Pole, the axis of rotation. So those are two different poles. The magnetic North Pole migrates clockwise or counterclockwise around the axis of rotation. And so there's also this small, what we call secular variation of the Earth's field that can be measured in lake sediments and loess's and give you very detailed ages of sediments, and can be used especially from pottery. Anything that cools locks in the Earth's magnetic field. Lava's cooling. A pot that's been fired in a potter's oven, as it cools, it takes on the Earth's magnetic field directions. Or sediments that are falling to the bottom of a lake. Little iron-rich sediments, minerals containing iron, will become aligned with the Earth's magnetic field. Think of them as iron filings, if you like. And so you get either a thermal or detrital remnants preserved in sediments. And that's what I work with, because I know the polarity history of the Earth. And so I simply now collect oriented samples from these beautiful till cliffs here in Lethbridge or Medicine Hat, take them to a magnetometer, and measure the magnetic orientations, the inclination, the declination, the strength of magnetization, and this is a vector which can be plotted and can be tied to this geomagnetic polarity time scale. Now the other measuring stick, if you like, that I can use for the older sediments is the isotopic record, a paleothermometer, if you like, where during glacial conditions or cold conditions, the lighter oxygen, there are generally two forms of oxygen in water, O16 and O18, small amounts of O18. During a cold period, a large amount of O16 is stored on land in the form of ice, and so the ocean is enriched in O18. So that ratio between O18 and O16 is recorded in the shells of marine organisms, and when they die and the shells fall to the bottom of the ocean and are buried by sediments, they keep a record of what that ratio was between O18 and O16. And of course, with modern ocean water, we can measure the temperature of the water and the ratio of O18-16, and we've been doing that for a long time. So again, you calibrate these ratios with modern values that you know, and you try and extend that back. You model. There are, of course, assumptions that are made in this, but it gives us, by and large, a swing of temperatures from warmer to colder, and then during interglacial conditions, the opposite happens. All that snow and ice of the Ice Age melts, so that oxygen-16 enriched material flows back to the oceans, and now the amount of O16 is enriched. So you have the fractionation of O16 and O18 in oceans and on land being a paleothermometer. So the last thing I need to explain to you, and sorry for this little bit of intro physics and geophysics, but I need to explain this to you so you'll understand my next figures. The cycling of the Earth around the Sun isn't always the same. Our orbit has an eccentricity that changes. Sometimes it's nearly circular, as you see there. Other times it's way more egg-shaped. And the other thing that happens is the axis of inclination that we're spinning on is sometimes a few degrees steeper and sometimes a few degrees shallower. And also, over time, we wobble on our axis, okay? Like a top that you get spinning on the floor, and towards the end it starts to wobble. Well, that's called the precession of our orbit. So we have three components: the eccentricity of our orbit, the obliquity of our orbit, that is the change of the axis we're spinning on, and the wobbling we have. And that determines how much of our head is facing towards the sun or away from the sun, and whether that's in the summertime or in the winter. And that really will determine whether climates are warmer or cooler. In much the same way that if you sit with your face towards the sun, you'll feel the warmth. If it's away from the sun, you won't, right? So the Earth is no different. And so our aspect towards the sun is very important in cycling of climate. And these are very regular cycles that are well understood. And we see this signal in the isotopic record and in all of the climate records. We see especially the two components of precession and obliquity. Eccentricity, the orbit where we're either egg-shaped or circular, not that important in terms of how much heat we get. Very weak signal. But precession and obliquity, very important, as you can see there. And now what's interesting is that the Ice Age cycle, a glacial-interglacial cycle, shows 100,000-year frequencies today. In the past, it showed 40,000-year frequencies. And those relate to these orbital cycles that were There are 23,000 years for the precessional cycles, there are 40,000 for the obliquity, and there are 100,000 for the eccentricity. And so we see those changes in the receipt of solar radiation on the Earth's surface translate into either colder periods, which produce ice ages, or warmer periods, which produce interglacial conditions. And we see this in cave dripstone, we see it in corals, we see it in ocean sediments, the same patterns of precession, obliquity, and eccentricity are shown. And so back to our two rulers that we use in measuring older materials, the Dello 18 record and the geomagnetic timetable, we can date sediments. And so I've been to these places that are marked with squares on the map, and you see it's mostly been in North America, although I've recently been working in Patagonia and have done some work in Africa and other places as well. But in North America, it's mostly been looking at the American Midwest, the southern Canadian prairies, and the mountains of BC, as well as the Arctic. And the reason I've looked at these areas is, first of all, the best understanding we had of the world's glacial history came from the American Midwest. And so all our glaciations have names like the Wisconsin, the Illinoisan, the Kansan, the Nebraskan glaciation. Those are the type sections where we developed our first understanding of the glacial history of the world. So I went there and did the magnetic measurements of those deposits and figured out what they were in terms of age. And then I went to the prairies to compare what I saw there. And I went to the Arctic, and I went to BC. As you know, even today when you fly to Europe, you'll be likely flying over Greenland, and you'll see that parts of the Earth are still covered by enormous thicknesses of ice. And at the height of the last ice age, all these areas in white were covered. And here you see another projection. You see that much of North America, all of Canada, was covered by ice except for the Cypress Hills and the Delbonite uplands and a small piece of the Yukon. Other than that, all of Canada was ice, and the ice extended far beyond Vancouver Island and Newfoundland even, and of course then Siberia. On that little inset, you see a map of North America. It's a gravity anomaly map, and you see some blues, which is low gravity anomaly, and reds, high gravity anomaly. That blue is still the rebound of the Earth's crust after it had been weighed down with this enormous pack of ice that you see in the bigger map. And so the crust is still rebounding. So you're having a negative gravity anomaly there. So that tells you that's where the thickest ice was. There were two banana-shaped ellipses there, one over Labrador and one over Keewachia. And the last ice age we had, the Wisconsin, had much of the ice concentrated in the middle of Canada, and that pushed ice all the way to Lethbridge and Great Falls. The only time that we had an ice sheet that was that extensive. The earlier glaciations did not get to Lethbridge. We have some gravity data that shows the magnitude of some of these ice centers. So what have these glaciations done? Well, they've left deposits. They've left erratics that tell us something about where they traveled from. They're far traveled. So we find granites. Look at the farmers' rock piles here. There are granites and gneisses and schists. They all come from Ontario and northern Manitoba. We know that the glaciers have brought those here. Then when the ice disappears, sometimes you get still quite a long, prolonged cold period, and you get frost cracks and ice wedges, as you see in that top picture. But generally, when we look at the Alberta landscape, we see this sort of feature. And what is it? Well, this is the hummocky moraine that forms when ice stagnates and melts down in place. The ice is full of debris, it's being let down, and so you get a landscape, and you've all flown across Canada and looked out the plane window and said, what are all these funny little hills in Saskatchewan, right? Well, these are hummocky moraine or stagnant ice features. My students sometimes tell me it looks like the Earth has a bad skin disease. But these deposits are made up of ground up clays and sands and gravels and rocks and erratics that are let down from the base of the ice, especially when it's dead. And those are the sediments from which I'm extracting this paleomagnetic record. It's difficult material to work with because, remember, to orient little particles, I need very, very tiny, fine dust-shaped iron filings, if you like, but the glaciers have left us a very coarse load of material. So one of the things I learned to do was to very meticulously pick the finer grained sediments and sample widely so I could discard bad sediments and keep the good ones. In the north, the problem was even bigger. Everything was frozen, so it was hard to sample. And when I managed to chisel a piece of permafrost out, an hour later it was melted and it was sort of flowing off the table. So all the orientations were gone. So you had to figure out how to collect samples in permafrost. And what we discovered was get a pump up there, cut a deep trench. We pumped salt water out of the Beaufort Sea and cut a deep trench and let it slowly thaw, and these sediments then would stay intact but would be thawed, and we could sample them. Many sediments also are tilted, so we have to measure dip and strike because we want the original horizontal position of these sediments. And then where there are basalts, which we love to have because they're dated, so if you have glacial deposits and a basalt and glacial deposits, you always drill the basalts, make cores that you can orient, and measure the magnetism. The best record that we found of Canada's glacial history came from the Tintina Trench, an extension of the Rocky Mountain Trench, Cranbrook Golden area, right up in towards the Alaska border. And it's a sediment trap. There it is. And so every time a glacier came across this landscape, it left a smear of peanut butter, I call it, of glacial till. And I would get to sections and measure it. Now, geologists take many measurements at many sites. You can't trust one site or just one measurement, right? Because glaciers have left a lot here and very little there. So you really need to work with detailed sampling strategies. And geologists then like to make what we call fence diagrams. Okay, so they have all these units, some are thick, some are thin, and they tie them together if they have similar properties. This is in Argentina. It would be very easy to make a fence diagram of those units. They're all nicely horizontal and equally bedded. But for example, my work in the Tintina Trench had much thicker deposits in some areas and thinner in others, and some units were missing. Some had fossil-bearing sediments interbedded between tills. Some had basalt, some didn't. Some had volcanic ashes, some didn't. But anyway, I was still able to construct these fence diagrams, and I went to hundreds of sites in the Yukon and on the Canadian prairies and in the Canadian Arctic and built these fence diagrams that show the stratigraphy from oldest glaciation to the youngest, measuring the magnetic properties and tying it into the geomagnetic time scale. Now, most of the deposits on land also have something that's datable, so you have tie lines you can connect it to absolute ages. Volcanic ashes can be dated, basalts can be dated, pollen tell you something about the time the plant existed, and so forth. So I've constructed then a master table showing all of the glacial histories of the sites I've studied in Canada, and found out that virtually all the cold spikes of the oxygen isotope curve were preserved in the Canadian glacial record. So every time it turns colder, somewhere in Canada there was a glaciation, but not always here in the southwest part of Alberta, not all the way here on the west part up against the mountains. Many of those early glaciations stayed around Hudson Bay and Labrador, and so the question was why? The other area I worked in extensively was British Columbia. Those large glaciers filled up most of the big valleys, the Okanagan and so forth. The ice pushed south of the 49th parallel, as you see on this map, into the upper part of Washington State, often blocking rivers, building huge lakes, Columbia Lake and Missoula Lake. These would periodically overtop the ice dams and create catastrophic flooding down the Colorado River and out into the Pacific. So there were enormous thicknesses of flood deposits in Washington that originated in Canada, and I was able to measure the magnetism of these sediments. Also, there are volcanoes puffing away in Washington and Oregon, so there are regular ashes to date. So this turned out to be an excellent archive of paleomagnetic history related to the glaciation of British Columbia. And in these sediments, there were often bones. At Logan Lake in BC, there were fossil fish. In Medicine Hat, there were mammoth tusks. In Patagonia, similar sorts of glacial deposits. There were volcanic ashes and bones and so forth. In the Yukon especially, there were rich pollen deposits that told us that the types of trees that were growing during some of the interglacials, for example, were very different from what grows there today. So in this way, you start reconstructing paleoclimate from a whole proxy of indicators, but you always need to have some geochronometer at work for you so you know when it happened. Soils are important. Soils form during interglacials. Now, believe it or not, we have soils in southern Alberta that are red like the soils of Kansas and Utah and Oklahoma. There's not a lot of places, but they're around. Now, what does that tell you about temperature? It was warmer here, right, at one time. And so here you see an example of a reddish soil. This is in the La Salle Mountains in Utah, where I've recently been working. And these are reddish paleosols that I've studied in Argentina. I'm trying to get a fingerprint of these paleosols, their degree of rubification, the degree of redness, the degree of alteration of clays, the degree of carbonate displacement, which is all a measure of paleoclimate. And this is the red soil here at Mokowan Butte near Beezer. Beezer is near Cardston. In the back you see our friend Chief Mountain. And look how red that soil is. I had a student who was in a pottery class in the art department, and she took some of this red soil and fired it, and it made a beautiful pot. So that tells you a red soil that has not swelling clays in it, but hematite, iron oxides, and maybe some kaolinite, so it's a non-swelling clay. Those soils formed right here in our backyard. So we have had interglacials with very different soils. But I still didn't have the whole story of the Canadian prairies, so I went to the oil companies and with the help of the Alberta Geological Survey, got the top parts of all their cores. They're not interested in the top sediments. They want the oil and gas at depth. So they let me sample the top parts of these cores, and I got the whole glacial record and stratigraphy worked out for the stretch from Swift Current to Regina to Saskatoon to Cold Lake to Edmonton. And there you see it. And you see there are 4 different colors of green, so there are 4 glacial deposits. They're all distinctly different in places separated by interglacial deposits. And I measured the polarity and found that the lower still only is reversely magnetized. Now, I should tell you that we live today in a normally magnetized field, right? North is at the top. But about 700,000 years ago, the Earth's field was reversed. Your compass north needle would point to South America at that time. And so the lowest till here in all these bore cores is reversely magnetized. So we know that it's at least 700,000 years old. Do we have any other dates for those younger tills? Yes, we have some volcanic ashes, and we have some fossil beds. So we're able to assign these glaciations to some of those cold peaks. So we start with the oldest one there, right at the Bruns-Matayama boundary, which is where the Earth's field reversed, where we went from a reversed field to a normal field, which we have today. So the first glaciation in Alberta happened then. And each of those blue spikes is another glaciation. And we have records for all of those. So in this way, using paleomagnetism and using datable materials, I was able to calculate the extent and timing of glaciations in the western prairies. This was a difficult task because paleomagnetism is a crude measuring tool. And I worked with a guy called Edward Erving, who had come from Blackett's lab at Cambridge. Blackett received a Nobel Prize in physics studying cosmic rays, and then decided paleomagnetism was more interesting. And in the 50s and 60s, of course, there was still serious doubt whether continents were drifting. Erving himself failed his PhD at Cambridge because he put forward the proofs that pieces of England had moved from India. And his grand professors at Cambridge said, well, Mr. Erving, that's a nice idea, but you're going to fail your PhD because there is no mechanism for moving pieces of India to England, and so he failed. Later on, of course, they were embarrassed when plate tectonics was demonstrated to be a reality, and Ted simply referred to them as fixists. He did get an honorary doctorate from Cambridge later. He worked closely with a guy called Ronald Fisher, who some of you may know from Fisher statistics. And they had to work out the statistics of paleomagnetism on a sphere. Instead of the linear Gaussian standard deviation, they had to work this out for a sphere and look at precision of small numbers of samples. And Fisher had looked at Oh, I think it was the issue of people pouring a cup of tea and whether they put the milk in first or the tea. And he had worked out the statistics for that. He was a geneticist and a mathematician. He was interested in just about everything Ted said. They'd been together at Cambridge. And there, I think in that picture, Fisher is trying to figure out how a rotary phone works. He was a genius. He was called Sir Ronald Fisher. So I heard many stories from Ted about him. Ted and I worked together for most of my career and published most of our papers are joint authored. Ted was really the father of modern plate tectonics, proved that paleomagnetically that plates had moved from a central continent that had, supercontinent that had split apart. And he demonstrated that unequivocally, and his name is associated with really modern plate tectonics, even though Alfred Wegener had proposed it, and many people before him had also looked at world maps and said, aha, these continents must have been together at some time, right? Probably some even took a pair of scissors and cut out continents and fit them together. Anyway, Ted said to me, why don't we try and fit all of your paleomagnetic stories from the Midwest and from the Canadian prairies and the Arctic and the mountains in BC and the Yukon together and see if we can draw a map of what happened to ice sheets and relate it to these orbital variables that control climate. And so we'd come up with this hypothesis called the Barendregt-Erving hypothesis, which we set about to test, which was that as the Earth went from 40,000-year climate cycles to 100,000-year climate cycles, we should see or find evidence for that on land. 40,000 years of cold periods would give you relatively smaller ice sheets. So Canada should have ice somewhere over the middle, over the Hudson Bay and Labrador area where you have the highest snowfall and where ice sheets will form. And it's when you switch to the 100,000-year cycles, which happened about that time when you switch from the Matuyama reversed Cron to the Bruns normal Cron, so about 700,000 years ago. Now we're getting 100,000-year periods of cold, enough time to build whopping big ice sheets, and those ice sheets would be big enough to get to Lethbridge and Calgary and even down to Great Falls. And can we demonstrate that, right? That was our hypothesis. And so, let's see, better push the right button here. And lo and behold, when we put all of these paleomagnetic records together that I had worked with Ted Erving, on the top left, you see that in the earliest periods that we were able to measure in the late Pliocene, so about 2.6 million years ago, you have ice buildup only in the mountains. They're not very cold periods, but enough to build ice in the mountains. If it's going to get cold, where's it going to snow? In the mountains, right? And so that's where you build your ice sheets. Then as you advance in time, these 40,000-year cycles deepen and get a little colder. Notice now there's an ice sheet over Labrador covering much of eastern Canada. As we advance in time again, get closer to today, that ice sheet becomes even larger. These are based on real data points. There's little red squares on those maps that are actual cores or outcrops where I measured polarities. And eventually you get to the bottom two maps on the right. Those are one showing the ice sort of with a nice ice cover. All of Canada covered by ice, you see, from Newfoundland all the way to off the coast of Vancouver Island. So we were able to demonstrate that, yes, these orbital cycles, which control climate, and had shown this spectacular switch from 40,000-year cycles to 100,000-year cycles, for which we still don't understand the exact reason, but the fact is we see it in ocean cores, we see it in corals, and we see it in dripstone. Now I could also demonstrate that on continents where we can also say something about the plants, the pollen, the types of animals that lived and so forth, existed in fact. And of course, when large ice covers such as this one in the lower right exists, you've really drawn down sea level, because not only do you have big ice cover on North America, but also Eurasia, and of course Antarctica and Greenland are even bigger than they are today in terms of ice cover. So sea level is considerably lower, and you also allow then a big land bridge to come into existence, allowing plants and animals and people to move from Asia to North America and back from North America to Asia and so forth. The glaciers also did a real number on rivers. They completely changed the drainage pattern in Canada. Previously, the upper parts of the Missouri River all drained through the prairies towards the north. Hudson Bay didn't exist. and you had no Mackenzie River, and the Yukon River actually drained south into BC. But the glaciers substantially rearranged all that drainage. We now have a beautiful Mackenzie River, and we have the Yukon draining north to the Bering Sea. We have the Milk River, which used to be part of the South Saskatchewan system, now draining into the Gulf of Mexico. So glaciers really rearrange drainage. Okay, so this is important. I wanted to tell you a bit about the practical aspects of my unraveling the glacial history of Canada and its impacts on our river systems, because that will tell you where gravels have come from, whether you have buried valleys, old channels that are now covered by a new layer of glacial deposits. So if you're prospecting for gold or diamonds, obviously it's important to know the provenance of gravels and the paleo-drainage systems. Oil companies now are extracting shallow gas from these buried valleys. These porous gravels are an excellent reservoir or sponge, if you like, complete with a glacial till seal. And so there are quite a few places where shallow gas is being taken from some of these old river valleys here. Sand and gravel prospecting. City of Calgary is always on the prowl for gravel to make concrete. We've been able to show them some of the buried valleys. The land bridge, as I mentioned, let's see, I think I have a pointer here. There you see it. Much of Alaska would be connected to Eurasia. These waters are only about 100 meters today, and so, whoops, if you lower sea level, there's no problem moving people across, or animals. And of course, the camels came across from Asia, the saber-toothed cat, the lion, and so forth. We now have them in the fossil record here. And so together with the till story of glaciations, we have the intertill history, the interglacial history and fossil beds, of which Medicine Hat produced the greatest variety of animal bones that we've seen anywhere. This work on the magnetostratigraphy of the glacial interglacial histories has been well received and published in Nature in a couple of papers. I was also able to go over to England and use it to show when the first peoples came from Spain and southern parts of Europe and moved across into East Anglia. So the first human bones and worked stone, human-made stone artifacts are between one glacial deposit and the next, and I was able to paleomagnetically date those, showing that the first humans came into England about 650 to 700,000 years ago. And again, this was written up in Nature. Recently a paper in Nature on my magnetostratigraphic work in Bolivia, where we showed that even during the warm late Pliocene period, the mountains, which were much higher than today in Bolivia and throughout much of the Andes, had glaciers on them. So the elevation of the land is important in the Cordilleras, in the mountains. And you can get glaciers at unexpected times if the elevation is there. And so we can start reconstructing the big picture paleoclimate when we have a magnetic record and when we have something datable, and if we can relate it to the master paleothermometer from ocean cores. I do some hobby research as well. I've tried to figure out which pass Hannibal used to get his elephants across to get to Rome. Again, there's a record he didn't take any diary, but a person later, 50 years later, followed his route and heard from the locals that he got his elephants across some big rock falls by splitting up these rocks, building a big fire, and pouring water on these rocks. They would break, and then his men could drag these boulders out of the way, and he was able to get these elephants over the pass that would be the easiest. If you heat a rock and cool it in the Earth's field, just like that lava in Hawaii, what do? You lock in the Earth's magnetism at the time of cooling. And I found that the magnetism of those chunks of rock that he fired and cooled had the magnetism of 200 BC, 214 BC or whatever, when he used his elephants to try and conquer Rome. So this is purely fun work. And of course, historians have been fighting over which pass he must have used. Actually, later on, we went back and did some DNA work from Myers and Boggs, and found he also had a lot of mules, and we found DNA of elephants and mules, so that was the same route, so we were pretty convinced. Anyway, that was just fun work. So the summary, as I think, have I used up my time yet? Not yet? Okay. So first of all, I've sampled tills, which most geophysicists would say, no, too coarse. The tape recorder isn't on there. Well, if you sample diligently and take the fine-grained materials and realize that some samples are not going to give you good data, you need to take a lot of samples, and I've been able to demonstrate that if I can get dipole directions, which is the direction of the Earth's field, it's a dipole, it's either north up or south down, right? It's one or the other. And if you can reproduce those directions, you can establish a polarity chronology. So you can work with tills. Then I worked out a magnetostratigraphy for the prairies, which had been very difficult because the history wasn't well known, and it didn't tie in very well to the American type sections, which also weren't very well studied. And then I tried to relate it as much as possible, the terrestrial record, the land record, to the marine record, the ocean record, looking at the many wiggles and polarity crons and subcrons in both environments, and found good matches. Then, of course, I've helped at various times with applied aspects of fingerprinting sands and gravels for the gold miners in the Yukon. They'll come to me and say, why is there gold in that gravel and not in that gravel? And I say, well, because that gravel was deposited by one of the earlier glaciations, and the glaciers were cutting into gold-bearing rock. Those gravels are from a much younger glacial deposit when the glaciers had already chewed away all of the gold-bearing rock. So you're not going to find gold in those gravels. Now the gold miners, of course, said, aha, so the glaciers have also scraped across these kimberlite pipes in Lac de Gras and so forth. And I said, yes, they have. Well, where are those diamonds? Well, they're all in Hudson Strait and off in the Atlantic Ocean, where the rivers, the meltwaters, would have carried this stuff. They say, no, too hard to get. We're going to keep mining up there in Lac de Gras. And so we do have good placer diamond deposits from bore cores. We see many little diamond indicator minerals and even small diamonds, but we don't need to go for diamonds in the Atlantic at this point because we can get them much easier on land. So obviously in prospecting, understanding the direction glaciers speared things and carried things is important if you're prospecting for lead, zinc, copper, whatever, because you can keep making measurements in these till sheets until you find higher and higher counts of indicators for copper or whatever and say, ah, that's where the deposit must be. The glacier, like a block of sandpaper, has gone over it and carried little bits and pieces of it, getting more and more diluted as it gets to Lethbridge. They did find little diamonds in Wisconsin and so forth that came from Lac de Gras, so the glaciers have really moved things around. But if you understand how glaciers moved, you can figure out where they picked up that valuable load. So prospecting, drift prospecting is called, the glacial till prospecting is used very much by Canadian geological surveys. So those are the applied aspects. Then there is, of course, finding buried valleys and sand and gravel prospecting. We know how important gravel is to us. And so those have been some of the applied aspects. And there's the hobby work on Hannibal and his elephants. And I'm also always fascinated by this hummocky moraine that covers all of Canada. All these little bumps. If you travel from here to Travers Dam, you come across all these little hills, right? And you start seeing the first ones there at Shaughnessy, and we now have a nice cut through it. So I'm trying to learn more about how these hummocky moraines were formed. And I think they're formed by basically the ice, the glaciers thinning until they're basically a pancake of ice floating on a shallow lake. The lake drains, and the ice, like a cookie cutter, pushes down, and the underside of the ice is quite irregular, wherever the crevasses have seen greater melting, and it just cuts a profile on these deposits. It looks like a whole bunch of knobs. In fact, in the US, they call it knob and kettle moraine. Here we call it hummocky moraine. So I'm trying to find out a little more about the origin of these from wherever I can find outcrops. So that I just consider hobby work. I think good researchers should have funded research that answer basic questions of science. There should be applied research which is of value to everyday life, and you should be able to do some fun things that you enjoy, right? Oh, I still have more. So, you know, we all have people who are very important in our life, and one was Dr. Archibald McSween Stocker, who was the first geologist to come out and map the glacial history of Western Canada and map the surface geology, which are all glacial deposits. He's the man on the right. And he would come out by train and spend the whole summer here with his family and plod along to all the coulees, found those bone beds at Medicine Hat, and he basically spent the next 30 years at Medicine Hat, you know, digging bones. And I became his field assistant. He swung by the University of Lethbridge when I was in the Cousins building and said, I need some help. So I said, I'm willing to help you. And I'm a farmer, so I know how to use a shovel and a pick. And it became a very good relationship, and we published many papers together on the stratigraphy of these interglacial bone-bearing beds at Medicine Hat. Saber-toothed cats and ground sloths and anteaters and tapirs and you name it. These animals that were going back and forth between Asia and South America, right? Camels. And the other person there is Hope Johnson. She was a war bride that married the meteorologist who was stationed during the Second World War in England and came back and got a job at the Suffield Experimental Station in Suffield near Medicine Hat. And she said, I'm not so sure I like Suffield. Imagine coming from London to Suffield. And he said, why don't you go walk in the coulees? It's interesting terrain here. And she had done a lot of botany and zoology, and she started finding fossils and all sorts of interesting plants. And she came back home, and he was home for lunch, and he said, well, how did you like your walk in the coulees? She said, I loved it. I really like this area now. I'm going out right after lunch again. And she came back with buckets of all sorts of material that she couldn't quite identify, but she had her books with her, and she's been a real help to, she's also a great artist, so she would draw fossils, and she's illustrated many fossil books and articles for us, and identified many plants, and has been co-author, is well known to the Tyrrell people at Dinosaur Provincial Park. Both of these people received honorary doctorates from the University of Lethbridge, so it's wonderful if you can work with local talent and experts who really love the southern prairies and have made it their game to try and understand what it all means. The other man who was important in my life was John Dormar, because he was a soil scientist at Ag Canada. And of course, as you saw from those red soils and many other colored soils, I needed to learn more about soils. How do you determine sort of what the temperature was under which those soils formed? We know that today we have these darker black Chernozemic soils, right? There were times when the soils were even blacker and thicker. That means wetter, more grass, more organic matter. But there were also red soils. There were brown soils. There were mottled soils. So there have been all these different climates. And he understood. He immigrated from Holland and worked on soils all over the world. And so I got a good understanding of soils from him. And he was also fascinated in the geoarchaeology of the prairie. So you see in the lower picture there, he's taken a group of U of L students. He was an adjunct professor. To the Majorville cairn and sundial medicine wheel and so forth with some of the native elders, and they would explain what they thought these things meant, and John would listen and write about it. We also found a lot of fossils in our travels in the Medicine Hat and Welsh Valley, Swift Current areas, and there John in the top right picture is showing my graduate student why these coprolites, fossil dinosaur droppings, or as the local farm lady called it, dinosaur doo-doo, have all these lobate structures. And John is explaining sphincter contractions in the formation of coprolites there. I don't think the student is interested at all. And on the lower left, you have our eminent vice president academic of the past, Seamus O'Shea and Judy, and John Dormar, and I can't quite see who else is in that picture. But we've had many wonderful trips to the spectacular outcrops in southern Alberta. I'm always thankful for the great motor pool that we had at the University of Lethbridge here. We don't bother with motor pools anymore. They're a lot of work and a lot of maintenance. Just joking, that was in Patagonia. That was actually a field trip vehicle we used. Well, with all of these glaciation and interglaciations coming and going, of course, the animals were always on the move, and especially the mammoth and mastodon. As the glaciers retreated from Alberta into Saskatchewan, we find the carcasses of mammoth and mastodon. Pretty much the dates match the retreat of the ice. They like the ice marginal conditions. And in South America, of course, you meet the wonderful Magellanic penguin who likes to come and watch you work and is totally habituated to humans. And you talk to them and you tell them you're from the other hemisphere and everything looks upside down here in the south. Orion's belt is sticking up instead of hanging down. And, she just comes and stands there and watches you and listens to you talk. And in the north here, you get visits from these wonderful critters, the bears. And as long as you are not eating your lunch at that time, they're probably just going to watch. And in Kenya, I worked with Diane Fossey in Rwanda. Again, there's glacial history right on the equator, on these high mountains. and was able to work out the magnetostratigraphy of the glacial deposits there. Unfortunately, she was killed during the last year I was there, as you know, by the poachers. And then Warner Brothers made a film. Diane Fossey was played by Sigourney Weaver, right? So I was there when that film was made as well. But these were the troop of gorillas we had visited with several times. They were habituated. They sort of were used to us, and we could work there. And so I thank you for giving a rambling talk about my magnetostratigraphy of glacial deposits in North America and South America and a wee bit in Africa and England.